I will begin. Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students. Just ask you to use this time wisely, Lord, that we glorify you in what we do. In your name, of Jesus. Amen. All right, guys, you got questions? What? 4.2. 4.2, number 7. And this is a training? Thank you. All right. So, number 7 of section 4.2 in Nicholson. Find a monic quartic all right, with, 1 minus I and I as roots. And I missed a very important thing in real polynomials, right? And then the question is, can do with cubic? All right. So, yeah. The basic theory to work with here is that if we have, let's look at this, I'll just write it out in detail. If I have f of x equals to, a0 plus a1x plus a2x squared plus a3x cubed, well, plus dot, 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 I'll just do it for a general one, a n x to the n, right? And first of all, he talks about those being roots, right? So what's the idea there? The idea is viewing this as a subset of these guys, right? And so we know that the evaluation homomorphism is defined, right, from this to this generally. But in this context, to say that 1 minus I or I are roots means that when we plug in 1 minus I and we plug in I, we get 0. My point is that you might worry that doesn't make sense because we only defined the evaluation homomorphism for, polynomials with coefficients where we're plugging in. My point is, if we can naturally view a real polynomial as a special kind of complex polynomial. It's a complex polynomial with special properties. In particular, one of them is that if this, if we plug in z, let's say, and if that's equal to 0, right, then take the complex conjugate of this equation, right? Since a sub I is in the reals, since we're considering a real polynomial, that means that ai complex conjugate is equal to ai again, right? Which means then that this just gives us a0 plus a1 z star. I guess I use bars in here, don't I? Stars or bars, you got to make a choice. I guess we already chose bar. Z bar plus a2 z bar squared plus an z bar to the n equals 0 bar, otherwise known as 0. So like the fundamental theorem is that if Z in C has F, curses, I can't write. State this theorem decently and in order. Theorem. For f of x a real polynomial, right, if f of z is equal to 0, then f of z bar is equal to 0 for z in the complexes. In other words, as you've known since high school, I hope, complex roots come in conjugate pairs. So if I say that 1 minus I and I are roots, then I automatically get, right. So these come along, right? And once you know that, it's a simple matter to construct the quartic by the factor theorem, right? So the factor theorem gives us, so we just do f of x is equal to x, minus I times x plus I times x minus 1 minus I times x minus 1 plus I, which of course we could also express as x squared. And in fact, we must do this, otherwise we have not found the real quartic, have we? So x squared plus 1, and this is actually nothing more than x minus 1 quantity squared plus 1, which you can multiply out if you want. In fact, you might need to, depending on the wording of the problem. So that's x to the 4th minus 2x cubed plus 2x squared plus x squared minus 2x plus 2. Finally, x to the 4th minus 2x cubed plus 3x squared minus 2x plus 2. If I have made a mistake, there you go. In fact, there's the unique monic quartic, which has those as its roots. So could you find a real cubic? Why not? Right, because they come in pairs, which means you have 4 roots, which means you have at least a 4th order polynomial on your hands. By the n root, remember we proved last class that for polynomial of order n over a field, it has at most n zeros. Yeah. Other question? You guys try and make me feel better about my day. I'm enjoying this. Ask me something else easy, please. Please, please, please. I should only assign easy problems.
Number 21
Well, I'm just kidding. This one actually should be harmless. 4.2, number 21. But you guys have to read it out for me. A is what?
3x cubed plus 5x squared plus x plus 2.
All right, and B was? What was B?
5x cubed plus 2x plus 3.
All right, and C was?
X cubed plus 9x squared plus x plus 6.
And D?
X cubed plus x squared plus 10x plus 8.
And each one of these, the question is f of x irreducible over Q?
Yes. Well, it says like in Q adjoint or Q of the following
No, AK, I mean, this is equivalent.
Same thing.
Equivalent to asking the question, is it irreducible in Q of X? Yeah. And I don't think about, well, funny, yeah. All right, so we have some tools to work with here. The greediest among those probably being, I mean, the two sort of go-to tools. I covered them last class. Let me just tell you where they are in your book here. Of course, Theorem 8, the Eisenstein criterion, which is very nice. Now, you might wonder, why is that relevant? Because that's about irreducibility z of x, right? But I think we have, let's see here. What he says in Theorem 6 is, Theorem 6 basically kind of connects these worlds, right? Theorem 6 says that f is irreducible in Q of x, in other words, in rational polynomials, if and only if it has no proper factorization in z of x. And I think proper factorization just means that that's his terminology to avoid, like the example I gave in class last time, like the factoring the 2 out. I think that would probably be in his terminology, improper factorization. Does he have an example? Again, I haven't had a chance to really unwind his section here yet in his terminology. So I'm speculating at the moment on that.
It talks about trivial factorizations.
Where's that?
Page 215, the very top.
There he's talking about integers. I'm interested in what he says about the factorization of polynomials with integer coefficients, zx. Just humor me here for a second. Let me just glance through here if I can't find it. Here it is. It's on page 218. If f is a non-constant polynomial in z of x, all right, then we say f equals to gh in z of x is a proper factorization if both g and h have smaller degree than f. All right. So my example of 2x minus 4 factors into 2 times x minus 2 or whatever in class would be an improper factorization in his terminology, because I factored a degree 1 into a degree 0 times a degree 1, and only one of those has smaller degree, not both. Yeah. In any event, there we go. F is irreducible in Q of x if and only if it has no proper factorization in z of x. The proper just rules out the pulling out a constant multiple. Yeah. It's kind of a nice language. All right. So we have that. And the other main tool we have to work with here is the, let's see if he has a statement of it as a theorem. Of course, there's the rational roots theorem, which I never use because I'm an idiot. I mean, rational roots theorem can be useful. But the two tools I'm going to try to use at the moment will be the Eisenstein criteria and also reduction mod prime. Okay. Okay, so is Eisenstein applicable to any of these? We had to find a prime that divides every coefficient. But it divides every next to leading coefficient, right? Is that right? What's the criteria for the Eisenstein?
A prime divides a sub 0 to a sub n minus 1,
Mm-hmm.
and it does not divide a sub n.
It does not divide a sub n, right?
P squared does not divide a sub 0.
Okay, so when you look at these, maybe Eisenstein isn't going to be a good tool. You got a 3 and a 5 here. You know, I mean, there's like a 5 and a 1, so There's a 1 here, so Eisenstein, There's a 1 here. Eisenstein's out, actually. These are not Eisenstein problems, quite clearly. Because there's no prime that commonly divides all the coefficients. So Eisenstein's not a good tool. So I think we're going to have to look at reductions mod. So what do you want to try out? We can try reduction mod 2. Sometimes it helps. Let's try Z2 x reduction. So in other words, f of x bar would be, you know, x cubed plus x squared plus x, right? That's no help. X factors out. So that failed. Let's try a Z3 x reduction. So, all right, f bar. Let's try it again. F bar x is what? Well, that's also going to fail because you see the reduction theorem says that it's irreducible over z and hence q if and only if it's irreducible over if and only if the theorem I'm using, guys, is that f of x in zx is irreducible if and only if well, is reducible. I'm not sure about the if and only if, provided. I should actually look up the theorem to make. It might be if and only if. I can't remember right off the top of my head at the moment, guys. I'm sorry, but we need f of x bar is irreducible in z px, and also the degree of f of x bar is equal to the degree of f.
So you can't get rid of the first.
I think that might be if and only if. Let me just settle this. I'm sorry. Now it does state it as an if-then. This is if this is true in z mod p, then. Yeah, so I'm going to, my language here provided is actually saying, that's a sneaky way of saying if all this stuff, then that is irreducible. Okay? It's not if and only if. In fact, your homework problem on the x to the fourth plus 1, I think it is, you're supposed to show that that is, it's not irreducible. I think it's not irreducible mod any.
Irreducible over z mod p for any prime.
It's irreducible, or it's reducible.
No, irreducible.
Is that my writing or the book?
Yeah, it's you. So you're saying show that it's irreducible over z mod p, but then I guess you're really wanting us to see, but it's still reducible over z.
That's not right. I think that's supposed to say reducible. That may be a typo. I need to look at that. See, because this theorem would seem to contradict my homework problem. It must be reducible. The point is, whatever prime you reduce it, it's reducible, which doesn't give you information about the possible irreducibility over q. That's the point of that problem. It's a counterexample to the if and only if of this theorem. Let it be announced that, which problem is it? Number 83. Note to self, I must correct the very grievous typo in problem 83. So sorry about that. All right, so anyway, getting back to the point, Z3 is out because that reduces the degree to 2. So what's up? 5. All right, here we go. Let's get nuts. Let's see here. So we got 3x cubed. The 5 is gone. Woohoo! Plus x plus 2, right? Now, thankfully, this is a cubic. So we can use the theorem that we went over last class, which is that it's, what is it? If it's irreducible, if it's a quadratic or a cubic, if and only if what? It has no zeros, right? So you can check for zeros. And here we can check that just by plugging, right? So like f of 0. We call it f bar. I'd rather call it f bar of 0. So f bar of 0. What's f bar of 1? What's f bar of 2? What's f bar of 3? And if you're smart, it's actually smarter to check. If you want to save yourself some time here, sometimes it's better to not use 3 and 4, but to use negatives. But like 4 is minus 1, So when you check minus 1 instead of 4, it seems like it's a nicer thing to do, right? So 0 is 2. 1 gives us 6, which is 1. 2 gives us 28. Okay, which is what? 3, right? And mod 5, of course. And then 3. $86, you say? Which is 1. And oh no, use minus 1. Use minus 1. So we get minus 3, negative 2, all right. So you, by the way, like this one, this is a good illustration. What's minus 2? Minus 2 is 3, right? So we could check this using minus 2. It would make it computationally like way easier on us, right? It pays off to use sort of like staggered representatives that have, they're smaller. Arithmetic, it pays off. Anyway, so there we go. That is irreducible by our theorem that if there's no 0, it's irreducible since it's a cubic. All right? So consequently, that's irreducible. This is irreducible over Q. Or in Q of x, if you prefer that language. So this one, B, let me suggest that we try Z2. At some point it's going to work, okay? So f bar of x is equal to x cubed plus 3. All right. Oh, man. You worthless piece of... Oh. That means that, of course, this can be written as x minus 1 times something in Z2. So it's reducible Z2. That doesn't tell us anything. And so maybe 3 will work out for us this time, right? So 3, we have f bar of x is 2x cubed. Plus 2, I'm already dead. Game over. X times 2x squared plus 2. It reduces 3. I mean, you don't even need to plug in values. You can factor it directly. So 5 is out. So it looks like we worked our way to 7 on this one. Unless you guys know another prime between 5 and 7. Let's see here. So this time the reduced polynomial is 5x cubed. Oh, it's just, I mean, I guess. Yeah. Fine. So f bar of 0 is 3. F bar, and you can sometimes get away with this, plus or minus 1. Let's try this out, yeah? So that's plus or minus 5, plus or minus 2, plus 3. This is a dangerous game I'm playing, but if you play it, you play it. So the pluses go with the plus. You gotta be careful, pluses go with pluses, you know?
Yeah.
So you got 10 with plus or which is not equal to 0. Great. All right. Then f bar plus or minus, I'm mad with power, plus or minus 2. And by the way, this is minus 2x cubed plus 2x plus 3. And so that's equal to minus of plus or minus 8 plus 2 times plus or minus 2 plus 3. So with the plus, I get...
How'd you get 8? It's 2 cubed times 2.
Did I lose my 2? Oh, sorry. So with plus, I get minus 16 plus 4 plus 3, or it's quite clear at this point that the plus minus notation is a bad idea. And it would be much simpler to just do one at a time, right?
Yeah.
So I'll stop that. I'm just saying, in principle, there exist problems where plus minus pays off, but this is not one of those. Fine, just plug it in. You guys tell me what it is. I'm tired. 47. Yeah, which is 5. And f bar minus 2 is still good. Which is adding 42, 1. And then f bar of 3. Yeah. Well, minus 2. Oh. Times 27 plus 6 plus 3. What did you say that was? Oh, then either 4 or minus 3, right? I'll do 4. So minus 2 times 64 plus 2 times 4 plus 3. Here, I'll go old school. You guys happy? Take you back to your youth. So this is 5. Well, minus 5, I suppose. But does it work? I don't know. I'm guessing. I think so. Well, I mean, the key here is what's 7 times 40? 7 times 42 is what? I'm sorry, 7 times 16 is what? So if I add 112 to this, I get that. So anyway, it's not 0. Yay, it's irreducible mod 7. Consequently, using the theory, that implies that it's irreducible over Q of x. At this point, I'm tired of these.
Imagine us. Man, we've got 2 more to go.
Yes, but I have learned this before. You need at least 4 for it to sink in properly.
Before, so you can do it so much
You're not going to see a question that's easy on the test anyway. I believe what you're using there is a tried technique I've taught you, which is reverse psychology.
That's exactly.
And I approve of it. Which means that, I don't know what that means. It's inconceivable. Let's see here. Will I or won't I? I don't know. Part of the thing working against you guys is when I actually finally go make a test is I forget what I said. So there is that to consider, you know. But other question? .241. Seems like a good problem to look at. Double inclusion. Oh, I'm sorry. I got you. I was thinking something else. I was thinking of like a set, and I couldn't see a set there. But you know, this problem, by the way, these ones are very friendly. They're all cubic, which means this method we're using will work for those also, the ones I haven't done. If it's quartic, it gets much fussier, because then you have to start searching for quadratic factors, and that you know, that can be subtle. Now, so here we have f and g monic, means the leading coefficient is 1 in the polynomials over a field f. This is number 41 of section 4.3. All right. We're supposed to show that f divides g if and only if the greatest common divisor of f and g is equal to f. We are hinted theorem 10. I will cautiously look at it. Theorem 10 tells us f and g non-zero polynomials in f of x where f is a field, then there exists a uniquely determined polynomial d satisfying the following terms and conditions. D is monic. Why is my phone, it keeps beeping on occasion. Not sure what's going on here. Is this stupid computer turning itself on and off? Oh, you got to be kidding me. Update my Windows. Oh man, that means this battery. This means that what that means is this wasn't really plugged in. And so what I just did was I drained my computer battery with my phone charging, which was dumb. All right, getting back to here. So D is monic. D divides both f and g. And if h divides both f and g, then h divides d. And d is equal to uf plus vg for some polynomials u and v and f of x. In other words, basically the Bezout theorem, or Bezout, whatever, it works here. So theorem 10 says that, basically theorem 10, among other things, says that there exists u and v in fx such that uf plus vg equal to d, and that d is what we call the GCD of f and g. All right, so let me start out with the reverse implication. So suppose that the greatest common divisor of f and g is f again, right? Well, let's see here. The greatest common divisor of f and g is f again. What does that say about?
Then can't you go straight to 0?
Yeah, I'm trying to decide whether I even need to do that, but I think you're right. I think I need to do. So yeah, so this is equal to UF plus VG, right? Which tells us that F, 1 minus U times F is equal to VG, right? For some U and V in the polynomials, right? Which is to say what? That, well, what does that say?
Oh, we're trying to get f divides g. So that's g equals something times f, right?
Yeah.
Um,
I mean, to say F divides G, we need to get that G is equal to some polynomial P, whatever, times F, right?
yeah.
I really shouldn't use P like that. Let me, H. P makes people think prime, and that's a bad habit to use it as a variable, so I'll try not to do that. It's not quite what I have.
We haven't used the fact that they're mono.
Oh. Yeah, F and G are both monic. That's a good point. Huh. Well, what's that mean? Huh. I'm not, the other thing I'm not properly harnessing here at the moment is the divisibility. I mean, D divides both F and G.
So does it just follow immediately? Since it's the greatest common divisor of f and g is f, so f has to divide both f and g. Because we're given that it's mono.
Let's see that again. So this, let me write it down. So you're saying, so this must divide both F and G, right?
Yeah, I mean,
which means that if I call that just D, let me call this thing D for a second. Okay, just for less writing. So if that means D has to divide F, right? Which means that F has to be equal to some polynomial H times D, right?
No, I think you can just say since D has to divide both F and G, D divides G, but D is F. That would really say, but like,
All right, I will
you go straight to it.
say what you said again. I'm sorry.
Okay, so the GCD of F and G is F,
Yeah.
which in our case is D, and we know D has to divide both F and G. So D has to divide G. But D is equal to F.
But D equals F. Right.
Okay.
Okay, yes.
So basically, theorem 10 says that if you find a GCD of two polynomials, then it will satisfy all four of these.
Right.
Okay.
So the other direction is the one so there we should suppose F divides G, and of course F and G, somewhere we're going to we didn't have to use monic yet. So maybe monic will come up in this direction, which is to say that G is equal to H times F for some H, right? But the greatest common divisor of F and G, which we call D, has to be equal to UF plus V. I'm just determined to use this for some. It may not actually even be needed, but I want it to be needed. But we've got G is equal to, so this says D is equal to UF plus VHF, right? So D is U plus VH times F. What's that say? Other way around. I think that says that. Yeah, but I guess that we already knew. Wait a minute, do we not?
Wait,
We didn't already know that,
we
did we?
knew that D divides F, right?
Yeah, but we also know that exactly.
Now we know that F divides.
So this gives us F divides D, right?
Didn't we already know since like D is the greatest common
But,
divisor?
right, by definition, D divides F. So what do we have? We have that F is equal to I'll say polynomial 1, sorry primes, what can I tell you? Polynomial 1 times D, right? And that D is equal to polynomial 2 times F, right? Because both divisible, and then that gives us that F is equal to polynomial 1, polynomial 2 times F. But we're over a field, so we get that the degree of F equals the degree of P1 plus the degree of P2 plus the degree of F. They both have to be 0, right? So that gives us that P1 and P2 are constants, but what constants are they? We hope 1.
We hope 1.
We're trying to prove D equals F. Right?
Oh, yeah.
That's our goal. So somehow we can use monic to pin down those to be 1. Okay, they're constants. I mean, I think maybe it's just, maybe you can just forget about degree. You know, I mean, I think degree was just kind of a rabbit chase. This right here already implies that P1, P2 is equal to 1. Since F is monic. So we then have things like P1 equals 1 over P2. I guess that's where this is helpful, because that shows me for sure I can divide, because it's a constant, so it's the only thing that's a unit over the polynomials. So then I could put that over into here. I feel like if I keep playing with this, I can get that it has to be 1. Maybe we have to. Maybe we just have to. Maybe if we just go back to the start and look at what we have and assess the damages, we can prove that it has to be 1.
Oh, wait.
Oh. Theorem 10. What does it say about D? Nah. D is monic. D is monic. Look, these are, you know, this is a constant. These are both monic. That forces P1 to be 1. D being monic is the thing that I couldn't. In fact, if we don't insist that D is monic, there's an ambiguity that's possible here. Because if you look at this equation, U and V could be adjusted like this. And you still have the same style thing, unless that, but that D being monic reduces a certain ambiguity there. But there are many, many units in the polynomials, so in principle you can multiply by any of those and you have a very much related relation. But anyway. Yeah, I wanted to assign one of these ones. The reason I assigned this problem was to make sure you guys had a chance to think about the extension of Bezout to polynomials. And let me show you something as we're leaving here. Bill, my brother, has a wonderful, and I think I might have showed you guys this before, but he actually has a Euclidean algorithm for polynomials webpage, which will calculate the U and the V here for, I forget which examples, but like check this out. See, here he has, here's A of x, here's B of x, x to the 5th plus 2x to the 4th minus x squared plus 1, and then B of x is x to the 4th minus 1. What he's going to do, I think, here is to divide one into the other. And, well, that he's basically, division algorithm, what it ends up being is the last non-zero remainder is the greatest common divisor of these two things. And then you can work backwards to find the U and the V in the same way we work backwards to find the Bezout thing. Like the calculation we do to express the greatest common divisor of two integers as a linear combination of the things going into the GCD, that's calculation holds for polynomials just the same. So like here, that is the Euclidean algorithm, successive division or I guess subtraction, I should say. And that gives us this. Here's the u, here's the v that actually times this times u and v times that gives me back the GCD, which is 1. And let's see, what are the other flavor choices? Oh, you can do it over Zn. Zn equal to, say 3. There we go. Let's give it a workout. So the GCD of these is actually x plus 2 over z mod 3, which of course is a field, right? I wonder what happens if we put 4 into this. Oh, yeah, he warns us. If n isn't prime, the algorithm may fail. Well, it says something, but it's not sure that that's meaningful. But you could try 17. I don't know, it's kind of fun to look at the greatest common divisor of these two polynomials over different fields and see how it changes. But anyway, none of these calculations I really feel like doing by hand. Not a one of them. I made the mistake of teaching linear algebra, which used this kind of polynomial division 2 years ago. This is actually used as a computational basis for interesting results in Curtis's linear algebra, this kind of polynomial technique. That book was not well loved by the students for some reason. Yeah. In any event. Thanks, guys.